Good evening, ladies and gentlemen. Welcome to Drink and Derive 2. This one is going to be the Uniqueness Theorem for Poisson's equation, which is kind of got a few interesting little bits and pieces in it. As I've said before, some of this mathematics is not easy, and my rules of thumb are necessary but not sufficient to get through it. And as I said before, the rule of thumb is step 0 to doing any successful mathematics is to have a drink. So today I have a rather cheap bottle of McGuigan Estate Merlot from Western Australia, which is, you know, I've had it before. It's pretty good. It's you know, full-bodied, flirty red, just as I like them, and it's going to help us significantly today. So. I can already feel the mathematical juices flowing. Let's get on with it. So, the thing about Poisson's equation is it's a very important equation that crops up in a lot of places. The way we're just going to write it down today is like this. The Laplacian operator on some scalar field is equal to some function for all points R belonging to some domain omega. And this equation crops up all over the place. Electrostatics is probably the first one you'll meet if you're doing a physics degree, for example. Sorry, jump cut there. That's my video stopped recording for some reason. I do apologise. Right, let's carry on. Okay, so right, Poisson's equation, yes. So we're solving the equation. Laplacian on scalar field is equal to any function. And it's also subject to the boundary condition that that function is equal to something else on all the points which are at the surface of that domain. So if we take just an arbitrarily shaped domain in 3D, then what we're talking about here for the G is the surface of it. So it's G at the surface. Let's get another colour here. And it's F in the interior. And what we're going to prove is the uniqueness theorem. The uniqueness theorem is very useful for many other proofs and for solving the Poisson's equation in general. Pretty good. So, the way we approach this proof, it's actually basically it's similar in nature to a proof by contradiction. We're going to assume that we have two possible solutions to our equation. And the uniqueness theorem, what it is, briefly, is the uniqueness theorem says that there can be only one. There is only one solution to any given problem posed in the Poisson equation for a given domain and a given boundary condition. And we will prove this by assuming there are two, finding a consequence of there being these two separate solutions and proving that they are in fact the same solution. So what we're going to do is we're going to call these solutions phi1 and phi2 are solutions. Okay? And that implies obviously that Laplacian of phi1 is F in the domain, and that Laplacian of phi2 is also F in the domain. And similarly that phi1 is G on the surface of the domain, and that phi2 is G on the surface of the domain. So far so good. And what we're doing next is to define a quantity psi. Yeah, Greek letters get confusing. You've got to learn to deal with it, you know, because this is another reason why it's good to do mathematics drunk. Because after a few pints or a few bottles of wine, the phi's and psi's will start turning into one another. And then it gets really interesting. Anyway, we're going to define this quantity psi as phi2 minus phi1. And that means that grad squared of psi, because the linearity of the Poisson equation implies that it's grad squared phi2 minus grad squared phi1, which is 0 on omega. and that phi equals phi2 minus phi1 equals 0 on delta omega. Sorry, this should be in. Yeah, so we've set up the problem. We've defined a quantity psi here, which is going to be, it's the difference between our two different solutions. And obviously, if they're both if phi1 and phi2 are both solutions, then this subtraction, will give you 0 for the Laplacian operator, because the first one will be f. This will be f. Okay, so this will be f, and this will also be f. And that is basically how the proof is going to go. So the first thing to do with this proof is to invent this quantity psi, which is two separate solutions, subtract it from one another. And the second thing to do is to consider this quantity, psi grad psi, and then the divergence operator applied to that. Okay, you with me? Okay. Now, probably from your early differentiation days, you remember the chain rule. And the chain rule works just as well for vector calculus. Now, I'm not a mathematician, actually. I'm a interested amateur. And so I can just kind of spout these things without any proof. If you want the proof, you'll have to look it up. It's pretty, it's a bit more difficult. But basically, chain rule says we're trying to differentiate a product of things. We differentiate one and leave the other, and then we add on differentiating the other one and leaving the first one. And the complication comes because we want the divergence here, because you see this psi is a scalar field, but grad psi is a vector field. So we're doing a scalar times a vector, which will be a vector field, and so therefore we can't do grad of it, we're going to do the divergence of it. And this is why the chain rule actually requires a bit of proof, and I'm just going to hand wave it right now. Okay, but here we go. I'm going to differentiate the first one, giving grad psi. This is the dodgy bit, you see. And there's your vector product, right? So the first one, we've differentiated this first term and left the second one, and we've times them together, times being a dot product in this sense, or an inner product, or a scalar product. And then we leave the first one, and we differentiate the second one. So, I mean, you should be able to see that that's roughly basically chain rule, okay? But like I say, it requires some involvement to actually work out that this is allowed to be a grad. Of course, it has to be a grad because you can't take the divergence of a scalar field. And for a physicist like me, that is good enough for jazz. So let's move on. Now, I'm going to just rewrite this as grad psi magnitude squared, because this is a vector field, grad psi, and we're inner producting it with itself, and that will give you the magnitude of the vector squared. Psi, and then div of grad is just what we call the Laplacian operating on a scalar field like that. Okay, so you can see that this is a scalar field. The Laplace function is a scalar field if the Laplacian was on a scalar field. And this is a magnitude. It's a vector times itself, so it's a magnitude squared, so it's all scalar. So this whole equation now is a scalar field, as it has to be, because you can see that what we wanted on the left was a divergence, and a divergence must give you a scalar field. Now, I said rule 0 in doing good mathematics was to drink. There are a couple of other minor additions to that, which I might talk about at the end, but rule 1 is definitely if you have a divergence and you're doing some kind of proof, you probably want to integrate over it. Just trust me on this, okay? So we're going to integrate over this divergence over the volume, and we're going to integrate it over the whole domain of the problem volume. And if you haven't learned this up, learned this before, look this up. This is going to be the divergence theorem, sometimes I believe called Gauss's theorem. And this is the most important thing for you to learn when you do vector calculus, starting off, because it enables a whole lot of stuff. What it says is that actually you can kind of, it's pretty intuitive actually. If you take a domain and you're integrating over the volume, if you're integrating the divergence of some vector field A, of some scalar field A, I do apologize, scalar, right? then what it says is that due to basically what the point of the divergence is, it says that that is equivalent to if you take the same domain and you integrate over the surface of that vector field. Sorry, it was a vector field here, wasn't it? Taking the divergence of a vector field, of course we are. My apologies. Right, if you integrate that vector field times the surface normal, which is the bit of the vector pointing out the surface, and you integrate that over the surface, not through the volume now, it's saying that the integral of the divergence throughout the volume is the same as just integrating the vector field times the normal over the surface. It's kind of intuitive. I mean, people who are cleverer than me will do a much better job of explaining this, but it's certainly something you should know if you do vector calculus, right? Or if you're trying to, like I'm trying here. I'm not succeeding very well yet. One day, right? So anyway, we take the divergence. We use the divergence theorem. That allows us to change this into a closed integral over the surface. So we're integrating divergence over volume, and we can change that into a surface integral of the thing inside the divergence, like that. Oh, sorry, and it's got to be times by, and this is a vector, so it's got to be times by the unit normal and integrated over the surface, over all the surface. Brilliant. So far we've got nowhere. Well, you might think that, but let's carry on. Now, we'll pull in our identity here that we just worked out, pull that in, and so we've now got the integral over the whole surface of, over the whole volume, grad psi squared plus psi Laplacian psi over the volume is equal to integral over the surface of psi grad psi times the surface normal over the whole surface. Great. Now, a couple of interesting points here. This, in general, is still pretty complicated. But what we should notice here is that, given our problem definition that psi is actually a subtraction of two possible solutions, this term, grad psi, is by definition 0 from the original statement of the problem. See here, grad psi is 0. And so that means that this is 0. Okay? And the other interesting point is that, remember we said that psi on the surface, due to the boundary conditions of the problem, is 0 as well. So this one here means that that lot has to be 0 because this bit there is 0. Psi is 0 at the surface, right? And so what we are left with is this integral over the whole volume of magnitude of psi squared is 0. And this is where we go back to kind of word logic. We've done the mathematics now, we've done the difficult part. Remember that if you have a squared magnitude, squared quantity in general, squared magnitude especially, unless it's complex, and we're saying this is not a complex scalar field, but actually there is a theorem you can prove where it's still pretty much true, but this proof doesn't in fact capture that, I guess. Oh no, actually I suppose it does, because this is a magnitude. Yeah, so I mean, in general case, anything squared is positive. But if it's a magnitude of a vector squared, even if that is complex valued, it's still just a positive number. Okay? So we know then that this thing here is positive. Right? It's positive over everywhere. It's positive, whatever the value of psi is. And so, I mean, grad psi can be negative in places, but the magnitude of grad psi squared cannot be less than 0. So we're integrating a quantity that is always positive over a volume, and we are getting 0. The only way to do that, and this is going to be a therefore, not a right arrow, because this is thought going on. I've had a thought, sorry. Every time you have a thought, you've got to drink. Therefore, we know that the magnitude of grad psi squared is 0 in the whole domain, right? And a few short steps from there, if the magnitude of something is 0, the only way to get that is if grad psi itself is 0 in the whole domain, and that implies that psi is a constant in the domain. But if psi is a constant in the domain, we can actually work out what it was. And it's the way you work it out is where you work it out for any differential equation. You look at the boundary conditions. What are our boundary conditions? Our boundary conditions are that psi is 0 at the boundary. If psi is a constant in all space, but it's 0 at the boundary, then this thing, again, implies that psi is 0 in all of the volume. And we are done. We have proved that psi is 0. And just to recap for those who you know, if you need to follow this along later, that implies therefore that the solution phi1 is equal to the solution phi2 everywhere, whatever they are. And notice that that's whatever they are, and also completely independent of whatever the source term, the f and the g, and the boundary condition g and the source term f were. Completely independent. If you have two solutions to Poisson's equation, they are the same solution. They are identical by this proof. So it's kind of a nice little proof. But why is that useful? Well, the reason it's useful is because often, I mean almost always, you can't actually solve any given specified Poisson problem analytically. And so this allows you to be sure that if you have a numerical scheme, for example, that solves a Poisson problem and it obeys the boundary conditions and it satisfies the source term in the domain, it guarantees you that you have the right answer. Okay, there is not two ways to successfully solve Poisson's equation. You know, even if numerically the methods look wildly different, they are in fact the same answer. And I think there's been several interesting proofs. I'm not a pure mathematician, as I say, but I think there's been several interesting proofs using this property to actually prove completely unrelated mathematical identities. So, you know, find two solutions to the Poisson equation in this particular setup. The uniqueness theorem says they must be equivalent, and therefore you've proved that if those two things look different, you've proved that they're actually the same thing. It's fantastic. Anyway, that was the Poisson equation. I'm going to have a bit more wine to celebrate our success. Sorry it's been a long time since the last one. But please, if you enjoyed this, if you've understood something a bit more from it, if you read the Wikipedia page on Uniqueness theorem and couldn't quite work it out and this has helped you, then that's fantastic. I'm really pleased in that. Give me a thumbs up. If you would like me to do other equations in the future, please suggest them in the comments. Or if you have further questions or comments about this, comment section is down below. And I would love to hear from you. So thank you very much, and I will see you next time on Drink and Derive. Now, I am a northerner. I'm a British person. This is Saturday evening. I am lonely. I'm here alone. Nothing to do. So what normally happens is, in that situation, if you're a British person, you'll order a curry. And so that's what I'm going to do. Cheers.